All right, good morning, everybody. I suppose we can maybe get started. And yeah, I guess this is a pretty good turnout. I'm pleased to see so many people here. I guess first off, obviously, what we're looking at here is the course webpage, and I assume that you're all in the right place for the Quantitative Geology course. Are there people here who are not coming from just taking this GeoPython course? Like, has anyone not taken GeoPython at this point? Okay. So that's good. Yeah, so I suppose then you all know who I am, and we can go through a little bit of basic course information to get started, and after that, get into the lesson for today. And I think what I'll do in going through the basic information about the course is maybe point out a few things that are going to be a bit different from the GeoPython course. One thing that won't be different is that we will still record the lecture screencasts. I probably won't do them as live streams, so that means it might sometimes take a day before I post the video online. So that's something to be aware of. But let's take a look here at the course information just in general. So first off, what's different here between this course and GeoPython is that we're now focused a bit more on geological problems. And one of the big points of emphasis in the course is going to be about converting equations into Python code and then playing around with the equations, making plots and things like that to learn about how different sort of common equations in earth sciences are used and how they work. So we're going to build a bit on what you've already learned in Python, and now focus a little bit more on geological problems and a bit more on plotting and things like that. We'll still be reading in data files and manipulating data, but it'll be a slightly different focus, as you will come to see. The format is more or less similar to the GeoPython course. The lessons won't probably be as long, and some of them will involve maybe a little bit more lecture than I sort of can try to make them interactive, but certain things I just need to talk about different topics. So the format, though, will be pretty much similar in that you can sit here on your laptop and follow along, at least for the interactive parts of the lessons, and then typically what happens is that we have then about half of the time left for you to get started on the exercise, and usually we stay here to assist you with that. So on the webpage for the course, you can find also the schedule for what's coming up in terms of the different lessons. We're running here in period 2 once per week. So yeah, if I go to the course details, you can see the info here. I suppose you can already find on WebOD where to be and when. So that information's here. The important thing to point out, besides our Monday class sessions, is on Tuesday afternoons we will have the work session where you can work on the exercises, and you'll have at least one course assistant present and myself when it's possible. So yeah, I think. Is there anybody who can't make this session at all sometime between 2 and 6 o'clock on Tuesdays? Okay. Okay, so only tomorrow it's not, okay. All right, because in the past we have had to reschedule. If we can avoid that, it's nice, but it looks like this time should kind of work for most everybody, so that's good news. We'll be here also in the exactum for the work sessions on Tuesday afternoons. So on the page, you can also find my contact information and also contact information for Lotta, who's sitting in the back, who I guess probably most of you already know from GeoPython. And we're both available by email, or we'll continue using Slack as well during this part of the course, and I'll show that in just a moment. Otherwise, there's no course textbooks or anything like that. Everything you need for the course will be available on the course webpage. And if you're interested to read a bit more, there are some recommended texts here, a few of them about Python, a few of them about general quantitative geology. applications and things that could possibly be interesting if you'd like to learn a little bit more about what we're talking about in the course. As far as the grading goes, it's more or less similar to the GeoPython course with one significant difference, and that is we have exercises, but we also do have a final course project in the course that's basically a combination of exercises 6 and 7, and this involves a little bit of writing. So I can show you a bit about that here. If you look on the course page, I just added the information here for the final report, so if you haven't refreshed it, you might not see this. But there is some information about what this final paper involves. Basically, it takes the things that you produce, the plots you produce, and the code that you write in exercises 6 and 7, and has you gain some experience with writing a short article in the format of like a scientific journal article. So you can think about this as like a sort of mini thesis in terms of its structure, or like a typical scientific article in the sense that you have an introduction, geological background, methods, results, and then some discussion section. This looks very much like if you've looked at journal articles, they pretty much all follow the same general template. The idea here, though, is that instead of writing this like just a report of what you've done in the exercise, it is supposed to be written in the style of a journal article. So there's some papers that you should read, and when you write the introduction, you should write it like an introduction to a scientific problem that you're addressing. This might be a little bit sort of unclear at this stage, but I can assure you that in 6 or 7 weeks from now, you'll have a better picture of what exactly that means. But the general information is already on the course page, and you can look through that in a little bit more detail if you'd like. I think there's even, in the very end here, there is this PDF of, well, I guess you can't really see that so well, but this is basically the score sheet that I use when I grade the final reports. And so you can see in here what should be in each section and kind of what would get you a good score in each of the sections. So in the methods section, for example, you could note that you clearly state the different methods that are used. So you should kind of describe the Python code that you've generated for each part of the exercise. And if you do that, then you should get basically full points for the methods section. So it's all spelled out here on the course page for you. And again, as we get closer, we'll come back to this in like the last 2 weeks of the course to talk a little bit more if you have questions about that. Does the sort of general idea make sense about this project, though? You'll all end up basically doing the same thing, so it's not like an independent thing. As much as I'd like it, it would be rather taxing to consider grading 35 different reports about different topics with different Python codes. That's quite a burden. So unfortunately, you will do the same thing. But the good news is that because you're doing the same thing, it means you can also work together in a sense. So when you're working on the code in those exercises, you'll be sort of going for the same thing. So you can certainly talk with your classmates about that. The other thing I want to point out about the course information just in general is that the course is also running together with I guess it's a course from Language Center. So you can get, if you would like, for your bachelor studies, you can get 2 credit points, I believe, of your English language credits. And you can see on the WebOD page that you can enroll for this integrated English language component to the course. I think it basically means you're going to meet with an instructor from the Language Center a few times to learn some things about science communication and science communication in English. It could be useful for writing the final report. If you haven't already gotten those credit points, maybe that's something you'll want to consider. And I was told that the instructor for that course will try to join us somewhere, maybe around 10:30. I think she's in the city center for the morning, but she'll come and introduce herself. And I think already 22 people are signed up for this integrated language component, so I think most everyone knows about the situation with that. But Satu will come here and give us more information about the integrated language piece at that stage. Let's see. I think that's most of what I was going to say about the general course information. Do you have any questions about general things? Yeah.
Do you know what's covered in the 12 to 2? Like that's what we've got.
The 12 to 2. Yeah, so this is the 12 to 2 time on Mondays is this integrated language piece of the course. So if you don't need the credit points for English as a foreign language, then you don't need to register for that part of the course. But otherwise, I think that's when that will run, is from basically 12 to 2 right after we're done here. And usually, since we're done with the formal part of the lesson by 10:30 or something like that, if you need to squeeze in lunch before that, it's not normally an issue. Any other questions? All right, so I was going to point out one other thing here in Slack. I don't really know how I can make my Slack much bigger. I guess I can, looks like. But it's gonna look kind of ugly. So I guess you guys have already been using Slack in the GeoPython course. You know the deal there. But if you go to the general channel on Slack, if you haven't been there in a while, it's a good opportunity to go and check that out. You'll find there are links here for 7 channels that we will use during the lessons for this course. So there's these QG week 1, week 2, etc. If you click on those, as far as I know, you can add yourself to the channel. I don't know, because I created them, and so I don't have the option to add myself. But I think you just click on the link and then you're able to access the channels after that. There's no way that we can easily make these default channels without making it also visible for the automating GIS processes course people. So it's best if you just go to the general channel, and in there you'll find a link from last week on Thursday with these channels for the Quantitative Geology course, and just click on those, and please then add yourself so that you can see if there's anything related to the lesson materials. As you know, it's likely it would be posted in Slack. And also, if you have questions, that's a good place to ask questions about the lesson that week, both to the instructors and to sort of general everybody in the course. In some instances, other folks, like other students, will respond more quickly than the instructors, so it's kind of a useful thing to post there, because you can get some help sometimes quite quickly in the Slack channels. But yeah, you all know the story with Slack, so we don't need to talk about that much more. Instead, why don't we jump here? So we'll go to lesson number 1, and our lesson for today is basically kind of introductory geostatistics, and I think it's going to be probably review for some of you, which is not necessarily a bad thing, but the focus of the lesson in general is to first introduce a few things from NumPy. We didn't really see much of NumPy in the GeoPython course. It was mentioned at one stage, I think in lesson 5 or something like that. When we first got into pandas, there was mention that NumPy was hiding underneath, kind of like matplotlib is hiding in the background when you're using pandas for plotting. NumPy is this numerical Python library that is under the hood in pandas as well. In our course here, we're going to need to use a few things out of NumPy, so of course we need to introduce a little bit of NumPy. We'll only touch really a tiny bit of what you can do with NumPy, but there's a few essential things that pandas can't do for us that we'll need from NumPy. So we're going to start with that, and then after that, just go through some general statistical terms. Not assuming that you've had any previous course in statistics, but it's mainly just terminology to clarify what certain things mean and to talk about certain concepts that we'll deal with in the exercise for this week. So of course at the end then we'll come back to looking at that exercise. So I think probably the best thing to do at this stage, if you haven't already, is to go to the CSC notebooks page. You should find that there is a new notebook that is available to you called Intro QG 2019. If you're already launched an instance of the GeoPython 2019, it's probably best to destroy that, because our lesson materials will only get copied to this Intro QG 2019. I guess they call it a blueprint. I guess your screen probably looks a little bit different than this, but I think if you click the link from, like if you had gone, for instance, here to this NumPy lesson and clicked on the lesson binder, it should take you to the updated, oops, not binder, the CSC notebook. It should take you to the Intro QG 2019 blueprint. I think otherwise, if I was to, maybe I can put myself in like normal user view. Yeah. So I guess you should see something like this: AutoGIS, GeoPython, and then you should see this Intro QG there. Is anybody not seeing that Intro QG thing? Okay. So yeah, like I mentioned, it's best to destroy the instances if you created them with the GeoPython. Sorry about not saying something at the very beginning about that. But yeah, this other instance, this Intro QG 2019, will automatically then update the lesson materials whenever we use whenever we use this. So that's the best place to start. You could also use Binder if you like, but again, Binder has about 10 minutes before it dies. If I start talking, I could easily consume that 10 minutes, so your Binder session might die if that happens. But once you've launched your CSC notebook, you should notice now that perhaps before we had these notebooks and exercises directories, there's now one here called Intro QG. This is to avoid conflict with the GeoPython lesson stuff, because we also call our lessons like lesson 1, lesson 2. So the Intro QG folder should contain a notebooks and an exercises directory, and that's where you want to go to get started. In the notebooks, lesson 1, there should be this NumPy notebook there. If you're not finding that or having trouble, perhaps you can let Lotta know, and she can assist with that. I'm going to make this maybe one click bigger, although I suppose you can see the projector is kind of fuzzy, which is unfortunate. But yeah, anybody having trouble so far? Yeah. Okay. I can't think of any reason why that would be. So when you you only see AutoGIS and GeoPython, or do you not see?
I see like the exercises and notebooks, but there's no.
Ah, the Intro QG folder.
Folder.
Yes. So did you?
I used the Intro QG.
You did use Intro QG 2019.
I can try it again.
Yeah, if it's not working, I would just say maybe use Binder for the moment, and then I can give you some help when we have a moment to do that. Any other, is anyone else not seeing this Intro QG directory? It should be kind of a pretty safe little script that we wrote to make the directory, so I think everyone should get it, unless you've made a directory called Intro QG already. Okay, if there's not issues, then what we'll do is we can, like I said, take a look at a couple things from NumPy. And as I mentioned a moment ago, this NumPy is a numerical Python library. If you're interested, you could, for instance, type in NumPy and go visit the website, and there you'll find a whole bunch of documentation about NumPy. So if you go here to the manual, there's a user guide, there's a reference guide that basically describes every function that's in NumPy. What this means is that if you're using something in NumPy and you want to know how it works, of course you can go to the web page and find a complete description of how things work. There's also this kind of starting user's guide. If you're interested to learn a little bit more about NumPy, they have things like a tutorial and some lessons here, or kind of at least materials you can follow along with to learn a little bit about how NumPy works. For our purposes, we really only need to know, I think, 3 things in NumPy. As far as I can remember, maybe we'll need something later in one of the other lessons, but for us, life is pretty easy. We're going to start just by importing NumPy, and you can do that by just running the top cell there to import NumPy as NP. You'll see this anytime NumPy is used pretty much anywhere on in Python. It's almost always renamed as NP. And in terms of the concept, the thing that we need to do in NumPy that we can't do in Pandas is to generate a list of numbers that is not something like what we would generate with the range function, but a list of numbers that might go from 0 to 2 pi in a certain number of steps. So if we're going to do things like calculate, for the example here, we want to calculate the sign of some value x. We want to define a list of numbers x where we're going to calculate the sign function, and we can do that using NumPy. The first way in which we can do that is using a function called linspace. So we can say, for instance, x equals np.linspace. And what you do with the linspace functions, you give the first value you want to start with. So let's say we start with 0.0. The value you would want to end with in your list of numbers. So this could be 2 times np.pi. So np.pi is just the value of pi, and it's a constant available in NumPy. And then you say the number of steps you want to take to go from 0 to 2 pi. So let's say we want to calculate those values at 10 different points. So we'd have np.linspace 0 to 2 pi in 10 steps. If you run this, nothing special happens, but we can print out the values of x. And what you'll see here is that we have 10 numbers, you can count them if you like, that start at 0 and end at, this is basically exactly the value of 2 pi. So you might remember we've seen things like the range function earlier in the GeoPython course, and the range function never includes the last value that you give it. So if you say range 5, it gives you 0, 1, 2, 3, 4, doesn't include 5. Linspace will include this last value. So often this is what we would encourage you to use when you need to make a list of numbers that starts at some value and ends at another value. Linspace is kind of the easiest way to do that. The difficult thing can be that in here, you just specify the number of steps. You don't specify how big the increment is between the values. So if you want to say, like, I want to know the values from 0 to 2 pi in steps of pi over 8, you have to think about how many steps do I need to have an equal division of the range between these two values. And sometimes that can be kind of difficult. There's a reason why we introduce a second function, and that's exactly for that purpose. But what you can see here is that we have this list of numbers called x in this case. If we add another cell underneath that, we could check out what the type of x is, just as an example. So I just hit the plus to add an extra Python cell under here. And if you look at the type of x, you see it's an ND array. So this is a NumPy data type for an n-dimensional array. Array is just a term for saying some kind of container. of values. In this case, it's all number values. And in contrast to like a Python list, this ND array contains data of all the same type. So you can't put like a string and integer and a floating point number together in a NumPy array. That only works in Python lists. So that's an important distinction to note. Part of the reason why these things are pretty efficient in NumPy is the fact that the data is all of one type. And you know that right when you start using one of these values. So if you have a million numbers inside your array, you don't have to check the type of each one of them to do something. You know they're all of the same data type. And that, of course, means that you can do calculations a little bit more quickly. So yeah, that's the linspace function. We'll have a number of instances like where we're going to want to calculate things, maybe not between 0 and 2 pi, but like today in the exercise that you'll get, we're going to calculate some values at different elevations between some starting elevation and a finishing elevation. And so you'll get some experience with the linspace in the exercise for this week. So yeah, I mentioned that's one thing we can do. And of course, once we've defined x, if we wanted to, we could calculate a value of y here and say y equals np.sine of x. So there's a sine function in NumPy, np.sine, no big surprise there. And if we run this, what we'll do is we'll just calculate the value of the sine function at each point in our list of numbers x that we had here. So if I run this and then print out the values of y, just as an example, probably you don't know offhand what the values of the sine function are, especially at these unevenly spaced increments. But perhaps you remember that the sine function starts at 0, and by the time you come back around to 2 pi, it would have come back to 0. And so we have basically starting at 0, ending at minus 2 times 10 to the minus 16. That's pretty close to 0. And so it looks like our sine function is working properly. If we wanted to, we could plot the function, and that would mean using some matplotlib things. But perhaps you can just trust me that this is the kind of right calculation of the sine function. And perhaps you can also see the value in doing this, that like once we create this list of numbers x where we want to do some calculation, we can then go to each one of those points and calculate something like the sine very efficiently with a NumPy array like this. And just the same as we saw with our array called x, the type of our array y is another one of these ND arrays from NumPy. So that's not probably a big surprise. If you do a calculation that involves a NumPy array, the resulting data type that comes out is a NumPy array. So yeah, let's take a look at one other possibility. And that is, let's imagine a situation where we want to, instead of saying we want 10 values between 0 and 2 pi, we want to specify the increment between the values. So if we said we made a new array here called x2, and this is going to be using a function now called arange, works quite a bit like the range function does for Python lists and things like that. Here, again, we specify a starting value and an ending value. So we can say start at 0.0 and go to 2 times np.pi, so same range that we had before. But now, what you specify in here is the increment between the points. So we're going to say go from 0.0 to 2 times pi in steps of 0.5. So if you want to specify something, you know, like I want to start with my elevations at sea level and go to 8 kilometers in steps of 1 meter, the arange function is an easy thing to use because you can specify explicitly what the step size is. And if we run this and then print out what x2 looks like, you'll see our output looks somewhat similar in the sense that we get a list of numbers here. But you can see that we start at 0, then 0.5, 1, 1.5, and so on, up until the point that we get to 6, and then the value of 2 pi is about 6.28, so it's not quite big enough for us to get to 6.5. So that's 6 is our last value in this list. So if you want to specify the increment, the arange function is the option for that. Looks very similar to linspace, so it can be kind of easy to mix the two up. And I think it just takes a little bit of practice to get used to which one you want to use. I will give you one warning here. So let's imagine a situation like this, where you want to go from 0 to 10 in steps of 0.5. Of course, 10 is nicely divisible by 0.5. If we run this to have us go from 0 to 10, of course, we're going to get more numbers here, but we come back to our familiar friend, the range function, in the sense that this last value is not included in the list of values that the arange function generates. So if you use arange to make some list of numbers like this, it is different than linspace in the sense that you don't get 10 included in the list of values here. So in the case that we looked at, just in a sort of hypothetical situation, that we want to go from 0 to 8,000, so from 0 kilometers sea level up to 8,000 meters above sea level in steps of 1 meter. We can generate a NumPy array like that, no problem. When we print it out, of course, there's going to be a lot more values, but NumPy is smart about this and only shows us the starting and ending rather than showing all 8,000 values that we would have here. But you can see, for instance, here, the same problem coming back, that the value 8,000 is not included in the list of values this arange function produces. So if you want to include the value 8,000 in that list, one trick that I sometimes use, it's maybe not a great idea, but you can make the value just a tiny bit bigger than 8,000. And if you run this, now 8,000 will be included in the list. So you're kind of picking your poison here. Linspace is really nice in that you start with a value and end with a value, and you guarantee you're going to get both the starting and ending points, but you don't necessarily know the increment unless you think about the spacing of the points there. And with arange, you can start and end nicely with a specified increment, but you have to be careful that your last value is included in the list of values that you produce with the arange function. Yeah, any questions about the differences between these two? Yeah. Yeah, I mean, unfortunately, the way, like, the arange function works like the range function does in Python, so it doesn't include the last value. So you're stuck with that kind of behavior unless you put in some kind of trick like this. To be perfectly honest, what I often do is I just use linspace and think about what the increment, or like how many divisions I need to get the right increment. So like if we went back to our linspace example here and said, like, let's go from 0 to 8,000. This is a fun one to do. Of course, naturally, you're going to think 8,000 is the number of steps you should take. But if you run this, you'll see that the step size actually isn't correct if you have 8,000 values between 0 and 8,000, because it includes both the starting and ending value. If you do it with 8,001, everything looks fine, and same kind of output that we saw with the arange function. The thing is, you have to think about this number here and how many substeps you need. 8,001 is not necessarily intuitive, and it gets a lot worse if you have like 342 values that then you have to go, oh right, I need 343 steps. It can be kind of, I don't know, there's no good solution for that. It's like you just have to think about which one you want to try and use and work around the limitations. Linspace is safer in the sense that most often you want to start and end with a certain value, and the space between, like, especially if you're doing a calculation with a function, the step size between the values is not necessarily as important as making sure you get the whole range of values you're calculating. So yeah, any other questions about these NumPy functions? As mentioned, you'll see them in the exercise today, so you'll get some hands-on experience with linspace in the exercise. and it'll come back regularly in what we do in the other lessons. All right, so one other thing we can talk about here is generating random numbers. We won't do this too much, but NumPy can generate random numbers, and it can be fun to play around with the random number generator for making plots. Like I think, used it in the first part of exercise 7 in the GeoPython course. I think you make this my candy plot or whatever, using this random number thing from NumPy. So you've actually seen this, but we could make some numbers here called rand. And there are actually quite a few options for making random numbers in NumPy, but the simplest is to use a function just called np.random.rand, and whatever number you give there, it will give you back that many random values. So if I run this cell with np.random.rand with 10, and then just print out what rand has in it, I get a list of numbers back. I'm guessing that you all get different numbers back. It is not a true random number generator as far as I know, but it's sort of pseudo random number generator. It's not just taking values off a list. It is doing a little bit more than that, but the point here is that we get 10 values back that are random between 0 and up to, but not including 1.0. So it'd be 0 to 0.999999 up to the machine precision. So get a lot of 9s after the decimal point if you want. But this gives us some random values, and if you rerun this each time, you'll see if I just run these two cells over and over, every time I get a little bit different set of random values. In cases where you want to to play around with things like the random number generation, this rand function is probably the easiest way to do it. But I will mention that if you go to the NumPy website, I've got the link here going directly to the random sampling part of the NumPy page. You'll see there's a lot of different options here for generating random numbers. You can get random integers if you want random integers. Random floating point numbers are what we have, between 0 and 1.0. But you can also generate, all kinds of other random options. If you want to pull values from a distribution, like we'll see the normal distribution later on in the exercise or in the lesson today. If you want to sample randomly from the normal distribution, you can do that, or from all different types of statistical distributions. So there's a lot you can do with the random. But the vast majority of cases, all you want to do is just generate some random integers between 0 and 1, or random floating point numbers between 0 and 1. Once we generated this, if we wanted to, we could make a candy plot, but I don't think we need to do that right now. So yeah, any questions about this kind of very basic NumPy stuff? We're going to stick with pandas for the way in which we load in data files, for the way in which we do a good part of the plotting. We'll try to do that also with pandas, in trying to kind of keep things a little bit more consistent with the GeoPython course. I'm not going to steer you down the NumPy path, which has been what has happened in the past. Because, of course, you can load files using NumPy. You can read in data files, but it has a slightly different syntax. You can do plotting with matplotlib, but it has a slightly different syntax than pandas plotting. So we'll try as best we can to kind of keep things consistent in terms of what we're dealing with the environment. So yeah, that's the kind of the end of the hands-on part for right now. I'm going to go over a little bit of statistical background stuff next, just briefly. But I'll give you maybe one more chance if you have any questions about NumPy stuff. Or if you're, interested in what else you can possibly do with NumPy, I can say a bit more if you like. All right, so let's jump back here to the course page. So lesson 1, you can see the material's already there. We've just gone through this NumPy introduction. And we'll move here now to this kind of basic statistical terms and concepts. At some point, I should probably update this to include the Finnish language terms just so that like you can see how the two compare. I haven't done that yet, but it's something I might consider at some point in the course, just to put some of these definitions also to have the Finnish language term for them in case it's more familiar. But the basic idea is that when we start talking about geostatistics, there's all kinds of different things we could apply basic statistical concepts to. Some common examples would be things like if you're going to date minerals in a rock sample. Oftentimes you have some number of minerals you would date out of a given sample, and then you get some distribution of ages. You don't, unfortunately, often get that the ages come back exactly the same when you take a handful of the same mineral out of a rock sample and you date it with the same analytical method. The ages always have a little bit of uncertainty and difference between them. And so we can talk a little bit about some of these terms just to kind of give a foundation for what we'll do in the rest of the lesson and exercise today. And the first thing is I just want to clarify the sort of difference between a population and a sample. So if we consider something like what we do when we go out and collect rocks in the field, we're taking a sample, right? We're taking some piece of rock back from a field area to the lab, crushing it, separating the minerals out, dating them, whatever. That sample is only a tiny fraction of the actual population of rock. If you want to go and say, like, let's go sample some, Neoproterozoic granites, I'm sure you could go many places in the world and find them. You're only going to find at the surface exposed a tiny fraction of the volume of that rock body, and of course that means that you can only sample a very small portion of it. The idea is that we want to go and collect a sample that is a good representation of the ages in that entire, if it's a pluton or whatever. So our sample that we collect is a tiny piece of the population. It's easier to think of populations perhaps not in terms of rocks, but in terms of other things. You could think about, if you filled up a bag with like letter tiles from like the board game Scrabble, you have the whole population of letters there, and you're just taking a single letter out at a time. That's your one sample that you're taking out of there. And you know the whole population in that case because you have the alphabet, and that's the kind of limitation on what letters you could possibly choose. We're not often sort of dealing with that luxury when we deal with natural samples and populations. So the idea comes back to saying that we want to get something that's representative. We don't want to go and collect one sample and date one age from some location because it may not capture the variation, the natural variation in ages within that rock formation. So we can consider here a set of what I will just call critters, different fossils, and I don't really remember the names of all of these little guys, but perhaps you can find your favorite, brachiopod or whatever you want on here. The idea is that this is what we could consider as one population. And if we take a random sample out of that population, it means we just sort of blindly reach into the bag of fossils and pull out a group of them. We could end up with two samples that look like this. So in one case, we have a selection of the fossils that are dominantly the larger fossils. Perhaps if we reached into the bag, this is something that could actually happen because more than likely you would grab something that's a bigger fossil than a smaller one. So we have one sample here that is dominantly large fossils, and the second sample, also taken at random, that's dominantly the smaller little critters. And in this case, you can see that neither one of these is really representative of the population. So this is one of the issues that comes up, is that when you take a sample, the reason that you want to go and collect a sufficient number of minerals to date or whatever is that you want to make sure that you get that full range from, like if we were sampling these little guys, we want to make sure we take enough fossils out of the bag to get the big ones and the little ones to make sure that we have a good representation of the size of these things. Of course, naturally, there are other things that might bias this situation, like certain fossils may or may not be preserved. But this is just simply a statistical anomaly that we happened in this case to have randomly sampled and ended up with small fossils which could indicate that maybe we need to take a larger sample in order to get something that is that's representative of the population. So that's the kind of general idea between the samples and populations, and of course you can read a bit more on the course page as well. Another issue, another sort of situation, another issue that could come up is that you could take two different populations and sample them and end up with a sample from both populations that looks similar. So many of the same creatures are present in both of these populations, and the random samples in this case are more or less identical, but neither one of them, again, is a very good representation, because here we're seeing that there are a lot of these kind of larger fossils like this, but only one in the sample. There's here, I think these guys are trilobites or something. There's a bunch of them, but there's only one in the sample. So another kind of possible place where you could introduce some kind of error is to take random samples that aren't representative of the population, and as a result, you would perhaps draw the conclusion that these creatures from this population and these creatures from this population are the same, and they represent the same kind of populations in general, which then might send you down the wrong path in terms of further interpretations you could make from that point. So yeah, starting point is just to think about taking a sample out of a population, and of course that's our very basic beginning for talking about anything statistical, is about how representative is our sample of a population. Now if we take this, we can also talk a little bit about uncertainty, and uncertainty is something that I like to sort of use the example out of the oil and gas industry for the reason why uncertainty is important. So if you are to go out in deep water and drill on one of these drilling platforms where you're like 3 kilometers above the sea level, above the ocean floor, the cost for drilling is about 350,000 euros per day, and operating the platform costs about 300,000 euros per day. So when you're doing the assessment about where hydrocarbons are deposited underneath the seafloor in deep water, you want to be pretty sure that you minimize the uncertainties that you're making, because if you make a mistake and you suggest that someone, or suggest that the team drills in a location where there is no oil or gas, it could be a several million euro mistake and could be the end of your career with that company for making such a mistake, if it's something that they feel like you didn't spend enough time trying to really assess the uncertainties in the data. And of course, natural data like seismic data that would often be used for doing this kind of assessment does have some uncertainty in it, and it's subject to interpretation. So it's possible to make mistakes like this, and these are pretty costly, so you want to try to avoid those, of course. So that's the general idea for the value and thinking about uncertainty. In terms of the concepts here, we can talk about a few different things. There's some uncertainty that we're going to have that's kind of random uncertainty, or what's referred to as random uncertainty, and then there's uncertainty that's referred to as systematic. You can see in this figure on the course page here the sort of illustration of these random and systematic errors, and when they are large or small. So the random error, when it's small, generally speaking, it means the points that you're looking at are clustered together tightly. So if you think of things in terms of like a bullseye here, and you're trying to date something that is maybe the age is right in the center of that bullseye, if you get ages that are all kind of clustering around that point, the random error that you're seeing there is small. You're getting sort of fairly precise measurements, right? This is another term that's often used when we talk about these things. So precise, all that's telling us though is that the random error is small. It doesn't mean we have the right age. It just means the distribution of points around the values that we're dating, for instance, or if we think of the bullseye here, they're all clustered tightly together. Now they may be clustered tightly together somewhere over here, away from the bullseye, away from the target that we're aiming for. So the random error is still small. The precision in this case is still good. It's small amount of variation in here between the points. But now we've got something that's not very accurate. So the systematic error here is getting to be large because our points aren't hitting the middle of the bullseye. They've drifted off here to the right. And so this is not an accurate measurement. If you were doing this, perhaps you would think, maybe there's a problem with my dating equipment. I'm getting very good measurements, but they're systematically off. Maybe my sort of standard that I'm using to calibrate the machine is not working properly, or I've got some kind of other issue with the dating equipment that's giving the systematic error. So the ages are all kind of shifted off by some constant value. Of course, you can have also situations here like where your random error is large, so the spread of the points is big, but they're still kind of clustered around the middle of the target for the most part. The mean value here would be sort of right around the middle of the target. Or you could have points where you've got a wide distribution and things that are off the mark. So you've got sort of poor precision and poor accuracy. Sometimes you can control for these things, sometimes you can't. If you go dating really, really young stuff, pretty much you're going to have to deal with having large random uncertainties because you're dating oftentimes things that are at the limit of the detection of the equipment that you're using. So you have to deal with having a little bit larger random errors. You just hope that the analyses are precise. Here's the challenge, is that this is what things look like in reality. We don't often have a bullseye. So how do we know if we have systematic error? That's something that can be difficult to assess. You can tell things like whether or not you have a large random error because you can look at the distribution of points. Is there a big spread between the values, or are they tightly clustered together? You can see that, but you can't see here the target oftentimes unless you have things like a standard that you're dating. If you've got a dating standard, then you know, okay, I should get an age of 31.4 million years plus or minus some small variation. And if you're getting back 45 million years every time you do your analysis, okay, now you can start to see that you've got some kind of systematic error. But if you're out collecting samples in the field somewhere where you don't know the age of the bedrock, of course that can be a problem because you don't always know what you should expect to get for your error. So that's something we have to live with, and of course there are ways to deal with things like the reason that a lot of dating laboratories use standards is to make sure that they don't have these kind of systematic errors in their analyses. So I guess probably you've seen some of these things before. You've probably also seen this, the kind of idea about when you measure something, how you should report that measurement. Typically, if we were to measure something with like a compass, if you went out and said, like what's the direction of some city from where you are, you could measure, on the compass. Perhaps it's got ticks every 1 degree. So you could say, okay, well, it's, 340 degrees plus or minus 0.5. In this case, we've got some uncertainty because you can't tell once you get between the ticks whether the value is 0.0436 or something different than that, because you can only tell with a tick every 1 degree. The kind of precision you can get would be plus or minus 0.5. So when we report some measurement like this, if we were to go out and either measure things like locations using a compass or date minerals, if we were to date them, we would report the mean age plus or minus some variation in the age from repeated analyses, or if we date a bunch of crystals, a bunch of minerals out of the same rock sample, we could report the variation in the age that way. So that's kind of typical way of reporting things would just be, take our best estimate plus or minus the uncertainty. Our best estimate in many cases would be just to calculate what the mean value is. So if we did take a rock sample and date 10 minerals out of it, we just average what the age we get back from those would be, and that's going to give us the mean. You guys have already, I think, some familiarity with how to calculate a mean value, so there's not really much to say here. Other than the mathematical description, it's just the sum of all of the values divided by the number of measurements that you've made. I guess, is this sigma notation familiar? Do you know that sort of summation. Yeah, okay. So so this is our way of calculating the mean. No problem. We know how to deal with that. If you're unfamiliar with the sigma notation, there is a hint about that on the course page. Now, what is often also nice to do is to calculate how much a given measurement deviates from the mean. So there's a value here called deviation. It's just labeled as D here. And that is if you just take some measurement xi, so some age that you've dated, and just subtract the mean value from it, you're going to see how far you are differing from the mean value. And that's a useful thing to do. But what's often done is to instead calculate something called a standard deviation, and I think you've probably also got some familiarity with that term. Maybe you've not seen the equation for calculating standard deviation, but here the idea is that if you were to calculate the deviation and sum these values, because they're all based on the mean, the sum of all the deviations would be exactly 0 if you add all the values together. So you can't use the deviation by itself to give you a sense of, on average, how much do the measurements differ from the mean, because the sum of the deviations is 0. That's why you'll see here for standard deviation that you take basically the same equation, but you square the deviation, so you always get some positive distance from the mean value. So deviation will give you a positive or negative value, how far away you are from the mean. The standard deviation is going to give you a positive value always for how far you are from the mean. And then if you sum those values, divide by the number of measurements, and take the square root, that's giving you then the standard deviation. So it's a little bit, sort of basic math here, but just to sort of show you why you can't just use the deviation. It's useful to think about it this way, because you might think to do this in doing the calculation otherwise. Now, with standard deviations, there is a sort of interesting, I suppose interesting is subjective here, but potentially interesting concept about when you calculate the standard deviation. There's basically two different ways you can do it. I think in what we're going to use in the course, we sort of assume you're going to take this equation number 1. But what this says is that if you have a single observation, so you've got one measurement, that you can actually calculate the standard deviation for that one measurement here and come back with some value. Now the value you're going to get back if you take that one measurement and subtract it from the average is going to be 0. But you do get an actual value back for the standard deviation, which says that you have one measurement and infinite precision, or 0 standard deviation. The reason for this modified version of an equation for standard deviation here is that if you have a single measurement, it comes back saying that you can't define the standard deviation. So here, if you take n of 1 and you get 1 minus 1, you get division by 0, which means it's an undefined standard deviation. And this is perhaps conceptually a useful thing because it tells you that you can't define a standard deviation if you have only one measurement. If you have some Python code where you're calculating a whole bunch of standard deviations, it's nice to maybe handle the case that you have only a single measurement by having it come back with this would give like not a number if you tried to calculate the standard deviation here, which is perhaps useful because maybe you don't want to consider a single measurement in terms of the standard deviation if you have some code that's going to do some additional processing after that point. Like we'll see some equations that are going to divide things by standard deviation, and if you have a standard deviation of 0, it's going to cause problems in your equation. So the last one to introduce here is just another way in which you can report. It's a measurement of deviation, but it's a little bit different. This is called standard error. Sometimes you'll see data tables that use standard error instead of standard deviation. I point this out as a sort of cautionary thing because basically all it is a standard deviation divided by the square root of the number of measurements you have. As n gets big, the standard error is always going to get small, which can give you the sort of artificial appearance of like smaller uncertainties than you may actually have in the observations. And in fact, this is not really a measure of the average deviation of one of your like ages deviating from the mean. This doesn't report that. this actually estimates more how well the mean value is calculated. So the more samples you have, basically the smaller the uncertainty on the mean value would be. So for small numbers of samples, you'll have a relatively big standard error, which means that the assessment or the calculation of the mean value itself is fairly imprecise. So what you're going to do in the first part of the exercise for today is actually to take this standard, the mean calculation, standard deviation, and standard error, and convert those to functions in Python so that we can use them in the rest of the exercise. That's the kind of jumping off point. I don't imagine there are questions about this, but I will offer you the opportunity if there are questions. All right, so one last thing here is about the normal distribution. I guess probably you've all seen this. Has anybody actually ever calculated normal distribution of some values? A few people? Yeah. So this is also something we're going to do in the exercise today, is we'll calculate or create a function for calculating normal distributions of, in this case, we're going to deal with volcano data, as you'll see. But basically, it's another way of graphically and mathematically representing uncertainty around a measurement. So this is an example of, just out of a textbook, of cinder cone angles. So I guess this is the sort of slope of the cinder cones. And so there's some average here, and looks like in this case sort of normal distribution of cinder cones with different slope angles. So what you see is that most of them will cluster around the average, but there's going to be some cinder cones with a shallower slope and some that have a steeper slope. And as you get further and further out away from this mean, you see that the number or the frequency of cinder cones in this data set would be going down more and more. Now, this is often assumed in a lot of the statistical work that's done in many different fields and sciences, that we have some kind of normal distribution of uncertainty. If you take measurements and you just use a compass in the field to measure strike and dip, you might have a normal distribution on the uncertainty in those measurements. And we can relate this to things like our standard deviation here graphically. So this is again just showing the same idea of these normal distributions with 1 and 2 standard deviations shown in terms of the width, or how much of this distribution would fall within 1 standard deviation and how much of the distributions within 2 standard deviations. And I guess probably you've also seen that, with this, this gives us a way to sort of say that, for instance, with 2 standard deviations, that 95% of our data would fall within 2 standard deviations, and these tails out here then represent only 5% roughly of the observations. So these are, oftentimes this is used to identify outliers in your data set. So, things that are out 2 or 3 standard deviations away from the mean aren't things that we need to worry about because they're potentially outliers. So we'll also deal with this in the exercise for today. All right, so what I'll do is I'll introduce that, and then I think that's kind of it for today, and you'll be able to get started working. Perhaps if Satu from Language Center comes, then she'll maybe introduce herself and say something quickly about the integrated language component of the course. But let's go here, before she arrives, to this exercise number 1. So you should find here, I think the exercise link for GitHub Classroom is not yet posted because I wanted to make sure the exercise was okay and not full of typos before I make the link live. So for the moment, you can look at this. It'll take maybe 5 minutes for the course page to update. Once we stop, I can put the GitHub Classroom link on the page, and it'll take a few minutes to update. So I started out with this sort of silly motivation. I don't know. I was probably up too late when I was writing this, and this seemed funny at the time. But this is I don't know, at least this has been my experience that you end up talking sometimes at Christmas parties or other family get-togethers to family members who think you should know everything about geology. And so, here we've got Uncle Ismo asking questions about the elevations of volcanoes, which is not perhaps something that any of us could rattle off right offhand, what the average elevation of volcanoes is globally. But it is something we can calculate, and so this is our motivation for the exercise for this week, is to avoid these sort of humiliating situations where you don't know something and your family members are making fun of you. So you can read through this if you're curious to see the sort of the whole situation. But basically, we have data that's been pulled from this Smithsonian Institution's Global Volcanism Program. It's a data set of Holocene volcanoes. I think there's something like 1,400 volcanoes that are in this database. And all I did was I took the Excel file that's available on the webpage and I just saved it as a CSV file. There's been no other processing of the data. So it's if you wanted to, you probably could start with the Excel file. But I've just made it CSV because it's easier for us to load CSV files in pandas. But yeah, it's a database of basically all volcanoes that have been active in the Holocene that we are aware of. And if you go to take a look at the exercise, I hope that it loads. There's basically 3 problems. They have a few different parts in them, but the first problem is essentially, as I mentioned, making some functions of these different equations. So we're going to make a mean function, we're going to make a standard deviation function, and you can see here that we're just using the form with 1 over n, not 1 over n minus 1, for standard deviation, and then a standard error function. And for this, for instance, since you have an equation for standard deviation, perhaps in your equation for standard error, you will want to use that standard deviation equation. So we'll make those, and that's kind of it for problem 1. You just make those 3 functions. You can see here that all of the tests are visible. So I was not super following what was going on in the exercises in the GeoPython course, but I guess you guys are familiar with running things with tests in the cells. Here we just left all the tests visible because we just give you some kind of junk age data sets or whatever numbers. It's just a list of 5 numbers, and you can test out your functions here and you can see whether you get the right values back. So this is basically just a way to know that your mean, standard deviation, and standard error functions are working properly. You, of course, could cheat and just make them return these values, but that's not going to help you in problem 2. So this is here basically as guidance for you. So in problem number 2, we're going to do some stuff with this data file. First thing is we're going to load it in. And it's pretty much standard thing. Loads, reading a CSV file, you can use a semicolon character as the separator because that's the separator in the data file, not a comma. Be aware of that. And you can skip the first row. Otherwise, it's just read it in, just like we did in the GeoPython course, and then there's some values and tests that you can run after that just to print out that your data file has been read in properly. There's a little bit of cleaning of the data that we can do. It's not really much. But the data set does include volcanoes that are below sea level. We're going to just knock those out, so we don't need to deal with any volcanoes below sea level. And also that there is a column in the data called tectonic setting. And there's a few nan values, a few not a number values there. So we can drop the rows that contain not a number for the tectonic setting. I don't think, come back to really using that, but we'll just do that in sort of good practice for cleaning the data up. After that, we're going to answer Uncle Ismo's question about what the mean elevation of volcanoes is globally. And so we'll calculate here the global mean, and then global standard deviation and global standard error values for all of the volcanoes in the data set. This should be sort of following along with lessons 5 and 6 from GeoPython course. One thing I'll note is that our functions will need you to use the .values attribute. So when you have a pandas data series, you can have the data series itself and it returns both the index and the numbers that are in the column that you're interested in or in that data series. For our functions to work properly, you need to take that data series and then add .values to the end, so you only get back the numbers from that column, not the index as well. Otherwise, you'll get some, I don't remember what kind of error message, but it's a nasty one, 40 lines of stuff in the pink box. So yeah, that's your note. Make sure that you use the dot values when you're dealing with this part of the exercise. But again, here it shows you, my global average volcano elevation is whatever you calculate, and the expected value is approximately this many meters. So again, you can check and see whether you've processed your data properly at that stage. Our next step is then to go and take advantage of a column in here called region. There are, I think, 19 different regions in this volcano data file. And for each region, we can calculate what the mean elevation is, what the standard deviation, etc. And so you'll do that here. You'll make some Python lists. Actually, the lists already exist, but you'll add some values to those lists for the mean elevations for each of the different regions. And then finally, well, maybe not quite, almost finally, we'll stick all this up into a pandas data frame. So you'll have a bunch of lists, and you'll just compile them all together in a data frame. There's some hints about how to do that. I don't think we did too much like just creating a data frame in the GeoPython part of the course, so this might be a little bit new, but it's easy. There's a data frame function to create a data frame from lists. You'll do this here, and you'll do it later in the exercise, and it's not too difficult. If there's a need, we can put a hint about how to create a data frame on the course page. But I think you'll figure that part out without too much trouble. And then it's nice because everything's in one data frame. You can then manipulate it pretty easily. So that last thing in here for question or problem 2 is just a couple questions, just checking in on what you found in your data analysis. Then the last thing in problem 3 is to make some plots of our data. So you've calculated all these different mean values and standard deviations. First thing we'll do is make a bar plot of all the regional volcano data. So you'll have 19 bars, and each one you can add then an error bar on top of them to show the uncertainty in the mean values for the different regions. So there's some instructions here about how to make your plot, and I think that should be more or less pretty straightforward. We haven't dealt with errors or error bars in the plots before, I don't think. Yeah. So there is this parameter called y_err that will allow you to put a value in there for an error bar. You'll see how that works and can ask us if you have questions about that. One thing I will say is that it's advisable to use this fig size parameter with your plots to make sure the figures are a bit bigger. So like 12 by 8 inches will make a nice size plot. If you don't include that, there's 19 lines, and the legend has 19 entries in it, and it just like covers up half the plot if you don't make the plot a bit bigger. So you'll see why it's good to make the plots big in this case. The next thing is then basically do the same plot, but instead of using standard deviation, to plot the standard error. And you'll see that the uncertainties look much better. It's tempting to want to use standard error to report uncertainty, but it's good just to show that that's not a very good idea in general. For part 3, we come back to making one more function for calculating things. It does not render nicely in GitHub, but on the notebooks for the exercise, you'll see a nice looking function for calculating the normal distribution or Gaussian distribution. There's things in here like x bar, which is the mean value, sigma, which is the standard deviation, things that are kind of maybe familiar on some level. And then there's a thing in here for x, and x in this case is supposed to be some distribution of points where you want to calculate your the normal distribution. And so this will be elevation in our case, and you're told what range of elevations to use when that comes. This will probably be a bit confusing, so we'll be ready to answer questions about this part 3 because experience has shown us that that's sometimes a bit tricky. Anyway, after you make your Gaussian function, you then can calculate the normal distributions for all of the elevation data for the different regions, kind of similar to what was done for calculating these mean, standard deviation, and things like that earlier, but you'll make a bunch of distributions for all the different regions. And then you'll plot that. And the plot in this case is pretty simple. There's a couple things you should add, like label the axes and add a title and stuff, but otherwise it should be not too bad. And then there's a couple questions at the end. So it's a lot of steps, but I think the steps aren't themselves like huge things. So there'll be a couple parts in here that are definitely going to be a bit challenging, but I think you guys are well equipped to handle the challenge. And compared, like, we changed the exercise for this year to actually deal with some real data file rather than some synthetic data set from years past. So I hope that this is maybe also a bit more interesting to interact with some real elevation data and to get some sense of how variable volcano elevations are, because in some cases it's a bit surprising that they're either quite variable or not as variable as you might expect.